Welcome everybody to this, the first of the hands-on tutorials connected with the various research themes of ACEMS. I'll be speaking today about multiscale models. I'm Phil Pollett, by the way, and we're broadcasting from the University of Queensland node. All right, so multiscale modelling is all about modelling systems that exhibit important features at different time and space scalings and/or space scalings. And one such example is this model for intracellular viral infection. And what's depicted here is a cell, and there are processes going on in that cell, and three important chemical species are identified here: the viral genome, the viral structural protein, and the viral template. And there are 6 key reactions in this what's called biochemical reaction network, and the rates at which these processes occur are given in that table, K1 up to K6. And what I want you to note initially is simply that not only these rate constants vastly different, they're of different orders of magnitude. In fact, vastly different orders of magnitude. Okay, so the first of the papers listed there, they considered how you might simulate a model for this process, and here's the result of one of their simulations. And what's plotted here is the abundancy of the structural protein, the genome, and the viral template. And note the ordinate axis is a log scale. And so what we're seeing here, immediately we see that the three quantities of interest are vastly different in terms of their vastly different orders of magnitude in terms of their numbers. So in a way, plotting these three quantities on a log scale is kind of good multiscale modelling, because we actually get to see them all and see their behaviour. If we were just to plot this in MATLAB without any attention to the scale, we would see, I think, the structural protein evolving in time, but the genome and the template will be smacked up against the abscissa, and so you wouldn't see the behaviour that's so clearly depicted in this graph. So we see a steady increase in each of them on their own scales towards perhaps an equilibrium value. So these are the features that we seek to describe in this particular model, the behaviour of these quantities, but they're occurring over different time scales. So if we concentrate on one scale, then we're going to miss the behaviour in the others. So today I'm going to be looking at a simple technique for identifying the most appropriate multiscale model. It's an analytical method, and I'll be looking at this example again, this intracellular viral infection example, but we'll be working together on a much simpler example. So that's the first part of the talk. The second part of the talk is going to be on simple growth models. So 2 parts. So I'm hoping for a bit of audience participation here. Right, so I learned about this model from these 3 authors. This is a paper that appeared in the Annals of Applied Probability some years ago. They analysed this model along with others and gave quite a detailed analysis of this intracellular viral infection model. What they do is they write down, as the other authors did, the 6 processes, and note in particular stuff is nucleotides and amino acids, and that you can see that the T, being the viral template, is a catalyst, right? It they're all swimming around in this sea of nucleotides and amino acids, and they pick stuff off this to produce the genome G and the structural protein S. All right, so, and there are the reaction rates there again listed. Now, the way that their approach, I'm not going to give full details of the approach, but to identify a scale parameter n, which in this case is K5, they chose to be K5, and expressed the other reaction rates in terms of n. Now you might notice, if you look carefully, that only 3 of them have been scaled or written in this way. The others haven't been touched. I want you to note also importantly that the numbers of the 3 individual types of species have been scaled. So the most abundant, but let's start at the other end. The least abundant, the template is not scaled. So x of t is just n of t. The next most abundant is scaled a bit, giving me xg, and finally the structural protein has been scaled by n, so the most aggressive, if you like, scaling. Now their methods allow me to take a Markovian model and let n get large, and then identify in the limit the most appropriate model, multiscale model, for this reaction network. I warmly recommend you to look at this paper. I'm not going to say much more about this model. We'll be working at a much simpler one in a minute. So this is the basic idea. We start off with a Markov chain model in continuous time. So the state vector n here is the numbers of individuals of the various species. And so nj is the number of molecules of chemical species j. I might add here that j is finite. If j could very well be infinite outside this context in other biological models, so we might consider countably many types of species. Now, I mention that now because I know that countably many types is close to the hearts of many of the associate investigators of ACEMS, and this process of Ball, Kurtz, Popovich and Rempala has not been generalised to the case of countably many types. So that's an open question, if you like. So we start off with this state, and then we scale each of the variables to produce these xj's, and each of them have their own scaling. So these alphas are non-negative real numbers. Typically, they're rational numbers. If the alpha j, say, is 0, then the jth species is not scaled. And we assume that we can write the reaction rates also in scaled form. And so we're replacing the ki's, which were listed on the previous slide in that example, with kappa i's. All right. And the art of this, and it is an art, as there's some arbitrariness, is to choose the right scaling parameter. It doesn't necessarily have any physical meaning. It's usually going to be of the same order of magnitude as the abundance of the most abundant species. Having said that, you might remember that it was K5 in the previous example, and that's the fastest reaction rate, okay, the biggest reaction rate. All right, so the art is choosing these alphas and betas in such a way that the xj's, the scaled variables, are all of order 1, and so are these quantities kappa, right, which you can think of as scale-independent reaction rates. Okay, so that's the idea. Let's apply it to a particular example. So I'm going to go to the blackboard now. I don't think anybody needs to make any changes. So this is a much simpler chemical reaction. We're right, yeah?
Yeah, just make sure that people switch to your screen that says ACEMS AQ so they can see the chalkboard.
All right, you've all got that? Good. Okay, so we've got 4 species, A, B and C, and I'm going to write down the initial numbers of those species. So 10 to the 6th for A, species B, none of them, species C, 10 of them, species D, none of them. And the reactions are, first reaction is 2A goes to B. Thank you for cleaning the board, by the way. Yeah. It's never seen such cleanliness. 2A goes to B. A plus C goes to D. And that's it. All right, so you can imagine you've got these million molecules of A and 10 molecules of C initially floating around in a beaker or something like that. And every now and again you get a pair of molecules coming together, doesn't matter what type. They come together in proximity and then they react to form either B if there are 2 A's or D if there's an A and a C. If 2 C's come together, okay, well nothing happens, all right? So I'm going to assume that per close encounter the reaction rates are the same. The production of B and D per encounter are the same. So your task out there in television land is to imagine what's going to be happening in your. Think about how this process may evolve in time. Think about it in your mind's eye. Imagine doing a mind's eye simulation. What's happening? All right. So, can you all think about that too? In this, there's quite a few people in the room today, and they're going to be thinking about it as well. So, if you've got any, you want to give a description, please just maybe type your name, and then we'll wait for your description. All right. So, if you would like to hazard a guess about what's going on here, right? You've got 1 million molecules of A, you've got 10 molecules of C. All right. You've got this reaction. What's happening over time? What do you think's happening? So there's no wrong answers, okay? So have a go. While you're doing that, I'll write down the Markov chain model, which old fools like me like to do. So we have the state of our system being the number of A, number of B, number of C. You think I've forgotten D? No, the number of D can be written in terms of the others. So can someone tell me what number of D is in terms of the rest of these guys?
So we have an answer from UNSW.
UNSW, answer from UNSW.
So the number in B will be 10 to the 6 on 2, and the number in D will be 10. Oh, no, not right.
Okay, well, no, but this is like in the long term. Yeah, that's interesting. That's an interesting insight that the number of D will be 10.
Yeah.
Right?
Yeah,
yeah, so can someone tell me how I can write ND in terms of NA, NB and NC? Thanks. Right. Ross to the rescue. 10 minus NC? Yeah? Okay. Same argument leading to this idea that you get 10.
We have a comment that says, I think reaction rate matters.
Yes, they do, but I'll remind you that per encounter, the production of B and the production of D are the same. All right. So they're either the same and something, and the same or something or other. It doesn't matter, right? So, any takers on how this reaction progresses?
I suppose at the start it'd be very, very quick, lots of A's bumping into each other to make B's. But eventually it starts to peter out as then you've got lots of B's and a handful of D's floating around. So it becomes rarer and rarer for A's to meet each other. So I'm thinking probably in terms of rate, it would just maybe more exponential.
Right, so you have a large production of A's initially, sorry, large production of B initially. So you're losing A at a big rate. And so the number of A is disappearing. You say it's an exponential rate.
As a guess, yeah.
That's fine. That's fine. What about C? How does that?
You probably mostly transfer at the start, I'd guess, because there's plenty of A's go around, so it's a high chance that a bump into A's at the start would have most of it happen immediately.
Well, I'm not sure I agree with that, but let me say why I'm not sure I agree with that. Choose two particles at random. What's the chance they're A's? What's the chance they're AC? Right, so there's a very much smaller, an order of magnitude different chance of capturing an AC pair. All right, so that's probably enough, unless someone's got some further insight about the... I think we all agree about the behaviour of A, but what about the behaviour of C? Well, Kurtz, Popovich, Rampala, Ball, they've come up with a method that will allow me to identify the most appropriate multiscale model. And I'm going to go through that. So first of all, we identify, oh, one thing I maybe forgot to mention, this 10 to the 6th and 10, right, that's just there to help us. If I'd written 10 to the 23 and 10 to the 17, which would be the right difference in order of magnitude, right, 10 to the 23, Avogadro's number, right, so we've got a mole of A, and you say, oh, 10 to the 8, 10 to the 17, that's another large amount, right? No, it's not. It's tiny, right, 10 to the 17 compared with 10 to the 23. So these are numbers, and I'm going to scale the reaction rates as well. They're going to be much, much smaller in practice. So 10 of C, 10 to the 6th of A. Right, so we identify N, guess what, the most abundant species. So N's 10 to the 6th. And we're going to scale A and B, because they're a similar order of magnitude, by using alpha A equals alpha B is equal to 1. So XA is going to be NA over N. XB is going to be NB over N. And I'm going to set XC just to be NC. So here alpha C is 0. So this is where normal chemical kinetic modelling, this is where this differs from normal chemical kinetic modelling, where you'd be scaling all the parameters and the x's would be the concentrations. Right? So you'd be scaling by a very large number, volume times Avogadro's number, to get me the concentration in moles per litre. All right, so that's the scaling here. And I'm going to assume, well, I'll write down the Markov chain model first. So we've got two kinds of transitions. The first, corresponding to reaction 1. So we lose 2 of A, we gain 1 of B, and C remains the same. And this occurs at rate. And these are the so-called infinitesimal.
Sorry, Phil, we've got a question from QT asking, can you please explain the alphas?
Oh, yeah. The alphas, if you were to, I can see it in front of me, if you go back to my last slide, you'll see the alphas are the, you'll see xj is n to the minus alpha j nj. Right, so alpha j equals 1 means I'm dividing by n. Alpha j equals 0 means I'm not dividing by n. Alpha j equals 2 means I'm dividing by n squared. But that's not happening here. Okay? Good question. Right, so the rate at which, these are the infinitesimal transition rates, is some rate, constant k1 times na choose 2. Let me explain that. So this is the rate at which the reaction A occurs as a transition rate of the Markov chain. So Na choose 2 because that's the number of ways of choosing a pair of A molecules. Right? They're not proximate yet, as it were, but that's incorporated into this K1. That will be inversely proportional to volume. All right? So to take into account this homogeneous mixing and then encountering one another. Okay, so that's the rate at which the first one occurs. I'm going to scale that K1 in a minute. But the other reaction, Na minus 1, Nb, Nc minus 1, this occurs at rate K2 times what? So reaction rate A plus C goes to D. Anybody? Na times Nc. Good. The answer is Na times Nc because that's the number of ways of choosing one of A and one of C. Na times Nc. Well, this is much nicer chalk. I'm using the blackboard, ladies and gentlemen. This is This is a beautiful thing. This is a rare beast at the University of Queensland. We managed to keep it. We mathematicians have an emotional attachment to blackboards. It's part of our tradition. We need them. All right. That's not controversial. Right? I suspect I'll get controversial. I'm well known for being controversial. All right. So K1, the Ki's I'm going to assume can be written as kappa I over n. All right. So these are and the Ki's, little Ki's, are both 10 to the minus 7. Right. They're going to be much smaller if in reality. But from this example, we've got 10 to the minus 7. So the little kappas are both kappa 1 and kappa 2 are both 0.01. So I'll put them up here, kappa 1 and kappa 2. They're a proxy, if you like, for this particular way of setting it up, for the usual reaction rates that you see in chemistry text. So how's it going in terms of this? Can people see the blackboard okay? Yep, good. Okay, so that's the setup. Now, the paper I mentioned, the Annals of Applied Probability paper, tells us what happens to this XA, XB and XC. I'm going to rub this off now and tell you what happens. Has anyone else got any ideas about what happens to C before I... No? Okay, over time. So, we let n go to infinity, and xa of t, for each t, goes to something which I'll call lowercase x of a of t, which is purely deterministic. It's equal to 1 over 1 plus 0.1 times t. Purely deterministic. xb, on the other hand, that converges to xb of t, purely deterministic. That's 0.05 t over 0.1 t. Now, purely deterministic. So I remind you that these scaled variables xa and xb are random variables. Indeed, by varying time, they're processes. xa, xb, xc is a Markov chain on a lattice, right? So they're dependent upon one another. In the limit, we get deterministic. So this is like a law of large numbers happening here, if you're familiar with the law of large numbers. But what about C? And when you see this, so this is kind of not surprising if you're used to chemical kinetics arguments, but this is the most interesting, and what makes the whole thing exciting. This converges. Now, I haven't said what the mode of convergence is. You can ask me if you like, sometime. But this converges to a linear death process with rate, with death rate mu of t is equal to 0.1 times xa of t. So this is a stochastic process at which the number of C reduces by 1. So it's going from 10 down to 0 over time. And the rate, as time progresses, the rate changes. So this is a non-time homogeneous Markov chain. And that's the rate function. So I think that's pretty interesting, useful, and would give you an idea that this could very well be very useful, and it has proved to be useful since that first paper. There have been other papers come out since then. You can easily find those. They're all fairly substantial, by the way, so there's a bit of reading there. You know, very large number of pages, but on the whole, very well written. So there we have it. So you can draw conclusions. For example, the number, xc, which remember hasn't been scaled, has a binomial distribution with parameter 10 and success probability p of t, which changed with time. Just reading off what we know, or what many of us know in the audience here, certainly, from standard theory of the death process. That's the success probability, e to the minus the integral 0 to t of mu of SDS. If you do the calculation, you get 1 over 1 plus 0.1 t. Right, it's xa, but that's by the by. It's purely. So, okay, I can write down the mean and the variance, etc. So that's it for the first part. I don't know how I'm going for time. 30 minutes. Good. I get to waste another 30 talking about growth models. All right. So I think I've got time to answer any questions about this.
What is the intuition behind all the randomness being squashed into one species? You start off with randomness for all of them.
Yeah.
Then
yeah, so the intuition is not so much intuition as the mathematical method. So what we've done is we've scaled A and B, but we haven't scaled C. So they're actually, in terms of space scaling, they're actually operating, and we've democratized things by bringing them on the same scale, just in the same way as that graph democratized the three species. We scaled one, we didn't scale one, we scaled the genome a bit and the template a lot, so that we could look at them together, right? So that, I believe, is the answer to that. So if you think about the real, what's really happening, okay, lots of A coming to B, reducing every million years, I don't know, maybe not a million years, but every so often, a C meets an A, right, and becomes a D. And then a little while later, the same thing happens, another C meets an A, but there's much less A now. Right, much less A. Okay?
So we've got two questions at the moment. So one from QT on what is the behavior for large but still finite n?
Good question. What is the behaviour for large but still finite n? So then we would be looking at how close is this limiting model to the actual stochastic process of x's. So the capital XA, XB, XC process, that's what's happening, really happening over time. We've let n go all the way to infinity to get our deterministic and linear death process. So for finite n, we'd be looking at second order result. A central limit theorem would be typical in this case, and that's been done quite recently, I think, by Leah Popovich. So that will tell you, and she does not just convergence result, but she bounds. So we're able to bound the difference in a standard probabilistic way between this limit process described here and the actual process of x's.
And the next question from UNSW. I'm not sure how we get these results, how they're obtained. I don't get why we can't get them without the rescaling. Could you please restate this?
All right. Okay. So I think I've already answered that question for Yege. The idea of the scaling is so that we can see the behaviour of the individual components more clearly. Okay. So it's not what's going on physically. This limit. All right. So if we concentrate on C, it's a linear death process, all right, with this rate. So I think I better go and look at some growth models since I've worked pretty hard simulating them. So let me now sit down and do a little bit of MATLAB. Sorry if there are any further questions, we can leave them to the end. And I'm going to set a simulation going and describe it. So I'm going to share my screen. All right, ladies and gentlemen, let's see. So what's going on here? So what we've got is a collection of 20 sites, and particles are being deposited at those sites independently according to a Poisson process with rate 1. So each of the sites has a Poisson process. So those green dots are seeing the arrival of a particle, the green arriving of. So we have independent Poisson processes dropping particles in on the 20 sites independently. So that the sites are behaving independently. They're collecting these particles. Now, what's being depicted here in red is the height, right, or the depth if you're thinking about it like this, but if you flip it up, it'll be the height, right? Now this might be considered to be a very crude model for the growth of, let's say, lichen on a tree or something like that, or drying coffee stain or something like that. Yeah, not to put too fine a point on it. But it wouldn't be a very good model, I think, necessarily. But nonetheless, we're interested just initially in this height function. So we can say a lot about it, can't we? All right, so if you can just go back, please, to the blackboard for a minute. And this process I'm going to call random deposition. That's what it's called in the literature. Why not call it what's called in the literature? Random disposition. And this red curve ht of x is the random height at time t at site x. So we have a Poisson process, so ladies and gentlemen, what's the distribution of this random variable? Poisson. This is obvious to you, but may not be obvious to everybody. Okay, so it has a Poisson distribution with parameter lambda t, where lambda is the rate of the process. I'm just going to assume lambda's 1 to make things easy. I don't know. Sometimes it's a bit more complicated to have lambda equals 1 because you never know whether you're squaring it or square rooting it. But anyway, leave it. Lambda's out of the picture. So it's Poisson. So can someone tell me what's happened to h of t x over t as t gets large? So this is the long-term rate of growth for this red height curve. Think law of large numbers, ladies and gentlemen. And more generally, lambda. Right, so 1. Good. Now what's more, so h of t x is roughly t for large t. Let's take t away and divide through by the square root of t. So we scale the fluctuations. This also has a limit. So think about that for a moment. I just want you to, for those who are not familiar with the laws of large numbers, this is a random variable over here, random height. The limit is 1, constant, non-random. This, on the other hand, may not be deterministic limit. What is it? Brownian motion. Okay. Brownian motion. All right. Let's fix x and look at the random variable htx. Oh, he's right, by the way. But anyway, htx. So what's the limiting distribution? Normal.
I haven't thought that far.
0, 1. Normal 0. Standard normal. So by that I mean convergence in distribution to a standard normal random variable.
But in x,
For each x.
it's the standard.
Or is it? Yeah. Yeah. So in particular, ht of x, the standard deviation, I'll write std of ht of x is t to the half. So we grow at a linear rate 1, but the fluctuations grow as t to the half. The variance is t. All right, so let's look at a more realistic growth model. So that was the random deposition model. A more realistic growth model is this ballistic deposition. And I'll describe that sitting down, with your permission. So I need to share. Oh, is it there? Okay, good. So the particles, if they arrive, so particles are dropping in the same way as independent Poisson streams with rate lambda equals 1. There's a difference in the way that they attach themselves to one another. So I'm going to go simulate a couple of particles. So green means we have an arrival. So it looks much the same as what we had earlier. The difference comes about now. No, not quite. So this arrival's got stuck. So the particles stick to the particle that they have incidence with. So they might be a green or a red. Green means they're not green and red particles. I'm just indicating that I'm colouring them green if they drop as in the random deposition process, but red if they get stuck. So this model is sometimes called ballistic deposition or sticky block model, right? So I'll get it going and we can see the wave front, the height function. It's going to take over from me in a minute. There it goes. So the height function will start to appear now, soon, I hope.
So Phil, what's the precise ball governing how this happens?
The sticking.
Yeah, it's just independent Poisson streams, but we're sticking.
Okay.
That's all there is to it.
So what does it mean we're sticking?
Well, you probably can't see the screen, but if it goes, if a particle passes by another one, it gets stuck to that one.
Can't drop all the way to the
It doesn't drop all the way, it just gets stuck. All right? So, if it's incident with the particle, it sticks to the particle, whichever it becomes incident with. So this is another height function here. All right, so let's look at some other simulations now. I'd like to make this a bit bigger.
These are the models used in protein model.
This a minute. Let's get C going. Can you all see? So this is the random deposition model, and for large T, that height process starts to look pretty jagged according to Liam Hodgkinson here, ladies and gentlemen in television land. All right, so there's nothing very... Here's our height function starting to appear here. All right, well, I'll stop that. I mean, that's pretty boring, actually. Hours of coding, but you know, it's like a nice amuse-bouche. It takes 3 hours to cook and 5 seconds to consume. All right, so here is the... Okay, now here's the ballistic deposition model simulation. Very simple to simulate this, by the way. Not that many lines of code, to be honest. Getting it all looking pretty, that's, as we all know, you know, getting things looking pretty. By the way, I used the SPY function from MATLAB to get this happening. I'd like the height curve to appear sometime. You can sit and watch these. I find that when I'm looking at a talk, I just get mesmerised by these simulations. There it is. There's the height function appearing. Now I've got one final simulation, and this is quite a...
But the sticking seems to have a smoothing effect.
Oh, this Jerzy Filar said that the sticking seems to have a smoothing effect. Let's have a look and see another simulation that will help settle that suggestion. I agree, by the way, but does everyone else? So the black curve there is a height function for the random deposition. The red one is the height function for the ballistic deposition. So with the smoothing effect, Jerzy, do you mean that there's smaller variation?
Yes.
Yeah. So you've got this black...
I don't know why.
You don't know why? Nobody knows why. That's a punchline. All right, so I'm going to go back to the blackboard now. Okay. All right, so the height function at time t. no longer distributed Poisson. Nobody has any idea about the distribution of h of xc. We might have a little bit of an idea about its behaviour. Now, I think at 1999, Timo Seppäläinen established the following fact, a wonderful result, that the growth rate, the long-term growth rate, is linear. And the rate, C1, is going to be bigger than 1, obviously, because things are sticking. It's stochastically bigger, this process. Now, if we did this, we'd have, as it turns out, according to simulation results anyway, infinity here. So what I'm going to do is speculate anyway what happens. So Timo's result, by the way, he actually proved this. It'll enable me to slightly correct what I've said here. So we consider a sequence of height function processes indexed by n. We scale time as n and space as n. And the limit, almost sure by the way, those who know what that means, almost sure limit can be written as t times some function g of x over t. Now the typographical error I made here is that's 0. It's what happens at site 0. Now this, it's important to note that this process of ballistic deposition is happening on the whole of the integers. Right? You'll note that my simulations do not have this. Right? They wrap around, so they're happening on a cylinder. So there's no real edge effects there, but it's just a finite number of states. And so this C1 here is just g of naught. Now, Timo Seppäläinen proved a lot of things. In addition, he had to work very, very hard to get this. Extremely difficult to get this. And gave some properties of G. But nobody knows what G of naught is. Nobody knows what C1 is analytically. There's probably bounds somewhere in a paper that I haven't managed to find. All right, so nice result. Let's look at the scaled fluctuations. So we take ht of naught, so at site 0, we subtract its linear rate c1t, and this time we're going to think about convergence, some t to the, I'll write t to the minus beta here. Do we get convergence in distribution for any value of beta? Right, so beta simulation results suggest, and my simulation results don't suggest this quite yet, but I believe my betters, that this value of beta for which we get convergence is 1/3. So t to the minus a third. And this limiting distribution is the so-called, there's two of them, GOE and GUE, Tracy-Widom distribution. Tracy-Widom distribution. And the GOE stands for Gaussian orthogonal ensemble. So this is the limit is conjectured to be, not proved, conjectured to be the Gaussian orthogonal ensemble Tracy-Widom distribution. Yeah, but Liam's asking a question.
So I'm assuming that this is, so the condition for this is initially flat.
Yeah, in fact, yeah, it's a seed at 0, I think.
Oh yeah, okay.
All right, so that's the way. But yeah, okay. What were you thinking of? Some sort of other initial condition?
No, just because it changes from GOE to GUE depending on...
Oh, good. Okay, so Liam suggests that this conjecture changes maybe to a theorem if you use a different initial condition. All right, have I got time to look at that? Plenty of time. All right, so...
It's a lecture, 1 o'clock.
Yeah, okay. Well, we can disappear. Now, if we look at this wedge, this is h naught x equals the absolute value of x. This is the sort of thing you might be. And we drop blocks down according to a similar process and look at this height function. So this is called the corner wedge growth model, if I remember rightly. If you were to look at an appropriate scaling, a la Timo-Seppäläinen scaling, you're going to get a parabolic limit here for this process. And it's known that this goes to GUE. All right, so this is for this corner block model. So that's known. I believe that's been proved. All right, so very important point to make is that this behaviour is believed to occur in a large number of growth models, namely the fluctuations are of order t to the third. Right, so if you work out it's a little bit difficult to work out the variance because I've got to know the variance of GOE. But a large number of growth models have this linear growth rate and also, well, actually not necessarily linear growth rate, but their normalised fluctuations are ordered t to the third. And we say that a model with this behaviour, it might be the Tracy-Widom distribution or this growth rate in the fluctuations, we say that the model is in the KPZ universality class if it has this property. And KPZ, for those in the know, comes from Kada, Parisi, Zhang, and that is the specific model for growth that was introduced in about mid-80s by those authors, where they took a partial differential equation in T and X, I think it's Berger's equation, and added white noise. Liam suggests stochastic heat. No, if you transform it, you get what's called the stochastic heat equation. And that's the preferred model for mathematicians, I think, because you can make sense of what it means by adding space-time Gaussian white noise. And the notion of cylindrical Brownian motion is important there. I'm not going to go into that now, although I've done a lot of background reading on it for this talk, which puts me in a fairly good position to be able to understand a lot of what's being said, at least in ACEMS. On the question, this is a stochastic partial differential equation, by the way, the KPZ equation. It's known to have this growth rate and this growth rate in terms of its fluctuations. I was going to say that there's a very good source of understanding stochastic partial differential equation, and I know that you're going to say, you think I'm going to say Martin Heira's book on stochastic partial differential equations. I'm not sure I agree with everything written there, But I think I agree with everything that Jasper Barr wrote in his honours thesis, right? So Jasper Barr did his honours project last year, I think, with Thomas Tamerer, who's here, and Ross McVinish as supervisors. And it's a really clear picture about stochastic partial differential equations, and in particular what's meant by adding Gaussian, space-time Gaussian white noise. I think I don't know if Jasper's out there in television land, but perhaps he should make this available more widely, but I had to beg Thomas for it. But I learned a great deal from it, and it's really, really good. It goes through things very, very carefully, Hilosita theorem, etc., functional analysis stuff, good background. And he explains cylindrical Brownian motion very well. In particular, explains, so Gaussian white noise can be written as allegedly written as a series of weighted independent Gaussian random variables, normal random variables, and the coefficients are from a basis of a certain Hilbert space. Now, what I disagree with, at least at first reading Martin Heira's book, is I don't think the series he writes down converges always. I think you need also a growth rate in terms of eigenvalues of certain operators on that Hilbert space. So anyway, Jasper Barr's thesis. It seems like a pity to end on Jasper's thesis, but let me just summarise what I've done today. Okay, so two parts. We looked at multiscale modelling, where we try to reconcile the differences in scale of variables that we're interested in, and we looked at stochastic models for chemical reaction networks, in particular biochemical reaction networks, where you do get vastly different orders of magnitude of reactants. And we looked at the paper, without giving too much details of the technique, of Bull, Tom Kurtz, Lea Popovich and Rempala. They provide a technique for approaching this question: what is the most appropriate multiscale model for this kind of Markov chain model? And we looked at a simple example of that. We also looked at growth models. We looked at random deposition, and we knew just from undergraduate mathematics what's happening there. But if we look at a very slight change where there's dependency among the sites, that we have a very interesting prospect of linear growth, which is proved, but the interesting prospect of the fluctuations being of order t to the third, but moreover, it's conjectured that we get this Gaussian orthogonal, there was an O there, orthogonal ensemble. By the way, that nomenclature comes from the theory of random matrices, where these distributions govern the eigenvalues of certain matrix ensembles. So that's why this nomenclature happened, and Tracy Whittam are the authors of this work. So well understood in random matrix theory. Some growth models exhibit this behaviour. We say that they're in the KPZ universality class. Almost nothing is known about higher dimensions, so spatial growth processes. So there's a lot of questions, a lot of excitement in this area, and thank you very much for listening.